Okay, in this video we are going to take a look at the mean body temperature, and we want to test if it's really equal to 98.6, which is popular belief for quite a long time now. A sample of 106 body temperatures taken at midnight on a particular day provided a mean of 98.2 degrees Fahrenheit with a standard deviation of 0.62 degrees. We're going to use the significance level of 0.05 to test the common belief that the population mean is 98.6. I believe this data really did come from a study that University of Virginia did to test this out, and really has been changing our idea of body temperature. Okay, so the popular belief is that the mean body temperature is 98.6, and we are testing that, and we're saying that it's not. That is our claim, that it is not equal to. So this makes this a two-tailed test. Our confidence level is 95% with a 0.05. Again, it's a two-tailed test. Our sample size was 106, so our degrees of freedom is 105. Now I'm writing T alpha divided by 2 just to kind of point out that this 0.05 alpha is being broken into both tails, so we would have 0.025 in each tail. I'm going to show you where I came up with this, going to the t-table. So when I go to the t-table, again, I'm going across. I'm looking at a two-tailed test, so 0.05 in our two tails. The second row is a one-tail, and it shows us that of course, we're going to have 0.025 in each tail. So it's one in the same column. But I'm going to tootle down here, and I'm going to find that all the way down I don't have a degree of freedom row that is labeled 105 degrees of freedom. So I'm going to have to go with the 100, the next lower one, and that would be 1.984. So that is how I came up with that value right there. Okay, so we're plugging into our test statistic formula. Again, the sample mean comes first. What we're testing, our population mu, comes second. So plug all of this in, and I come up with a super low test statistic, negative 6.64, and we can see that that is not going to be, that's going to be in that lower tail far below negative 1.984. So just looking at that, we know that. But when I go to draw the curve, it would look something like this. We've got two critical values. It could have been down here or up here. Our test statistic came very, very low. When we start looking for our actual specific p-value, we get far, far below 0.05, and we'd have to get that with StatCrunch to be exact. I guess what I want to point out is I've got this test statistic of negative 6.64, and if I go back to the t-table and I'm looking at that row of 100, I can see that as I go across from left to right, my t-scores get higher, and again, they could be positive or negative, but I can see that negative 6 point anything is not even on the table. So when I follow this back up here to look at my top row, higher p-values to very, very small p-values, I know that it's even smaller than the rightmost t-value on this chart. So going back to this, that's what I'm referring to with this statement right here. But if you need to find the exact p-value, you're going to have to go to StatCrunch. So I will do that now. So I'm going to go into StatCrunch. I'm going to go down to t-statistics. We've got one sample with summary, and I need to put in our sample information, which is 98.2 was what our mean sample was. Our mean standard deviation was 0.62. and our sample size was 106. Okay, we're doing a hypothesis test, testing whether or not the mean is actually equal to 98.6. So we might come up with something a little different here, simply because we are being exact with the 106 and the 105 degrees of freedom here. But we come up with the test statistic of negative 6.64. Our p-value, it's off the charts. Whenever you have this less than 3 zeros and a 1, it's extremely low. So this is a low p-value, so this is proof that the null must go. This t-statistic is way to the left off, so that was another one that gave us the insight to say that the null must go. But being I'm in here, I'm going to go ahead and do the confidence interval. So I come down here to the confidence interval. Now again, this was a two-tailed test, and we were testing at the 95% confidence level, which matches up with what we have here for our default. So I can leave this as it is. This is going to put two 0.5% in each tail, which is what we needed to do. So we come up with a confident lower limit of 98.08 and 98.32. And when I go back to my table here, I think I made an error when I wrote down the 8 here, but 98.08 mu, and our upper limit is 98.3832. I'm not sure if I got that with the calculator or with StatCrunch. But in either case, 98.6 does not even fall in this interval. So all three methods prove, I shouldn't say prove, but they support that we should reject the null hypothesis. There is sufficient evidence to support the claim that the mean body temperature is not 98.6.